Ethereum needs you. Ethereum's developers are working on the platform's next major upgrade, and for the first time ever, ordinary, non-technical people like you and I can help take part and make that update a reality. But the time to do that is running out. If you want to get involved, you need to do it in the next few days. But what exactly is this opportunity, and how can you take part? Well, I'm going to explain all of that and more right here. Before I show you how you can get involved in this opportunity, I should probably explain a bit about what it is. What you'll be involved in is called the KZG Summoning Ceremony. Now, I appreciate that's a bit of a weird and fancy name for something that probably doesn't mean anything to most people. So what is this? Well, the short answer is that it's a trust-minimized process for creating a new cryptographic protocol that Ethereum is going to use after its next major update, which is called Proto-Danksharding. That update is focused on making Ethereum a better home for Layer 2 platforms, which will in turn improve scalability and bring down fees for end users. But again, a lot of that probably sounds like gobbledygook to most people. If you're confused, stick with me here. To really understand what this update is about, we need to have a little bit of background information. If you paid any attention to crypto in the last bull run, then you probably heard a lot of people saying the same thing: Ethereum sucks. That's because during times of high demand, Ethereum transactions are both slow and expensive, especially when compared to competitors like Solana. You might assume that this is because Ethereum is older than the cheaper blockchains and therefore has worse, outdated technology. However, that's not the case. In reality, Ethereum's poor performance and high fees are entirely intentional. You might think that's crazy. After all, why would anybody choose to provide a terrible user experience? In reality, it's because Ethereum is simply prioritizing something else: decentralization. There's a lot that could be said here, but I'm going to save most of it for another time. What you really need to know is that Ethereum is designed to minimize the barrier to entry for anybody who wants to take an active role in the network. In practice, that means Ethereum software must be able to run on all sorts of computers, including fairly cheap and low-powered ones. Therefore, Ethereum blocks cannot contain a large quantity of transactions or data, because that would overwhelm those low-end computers. As a result, it doesn't take a significant increase in transaction volume to saturate Ethereum's blocks. When that happens, users are forced to outbid one another to ensure their transaction is prioritized and included in a block. That very quickly spirals into the sky-high transaction fees that we all love to complain about. Of course, Ethereans recognise the problem here. They don't want to have a platform that anybody can help run but only the rich can afford to use. And so they've come up with a plan to help address that problem. A plan that will allow them to retain the accessible, decentralised nature of Ethereum, while also increasing capacity and reducing transaction fees. And that plan is called layered scaling. Layered scaling is ultimately about concentrating as much activity as possible into the smallest number of Ethereum transactions. The idea is to shift most day-to-day transactions away from Ethereum and onto new Layer 2 platforms. These platforms are built with performance in mind, ensuring transaction fees remain low even when demand is high. Every so often, all of the recent L2 transactions will be batched, compressed, and represented in a single Ethereum transaction. In this way, all of the activity still takes place on the Ethereum blockchain, just in a less direct manner. All the same, it means that all of the L2 transactions are still verified and secured by Ethereum, which leads to the ultimate win-win scenario for end users. They still enjoy all of the benefits of Ethereum and its robust, decentralized design, but they don't suffer with its low throughput, slow transactions, and exorbitant fees. Years of research have convinced Ethereans that layered scaling is the best way to scale a blockchain and reduce fees. But the problem is, Ethereum wasn't built with this philosophy in mind, and so some modifications are going to be required to get the most out of this more modular design. One of the biggest issues is storing data. Remember how Layer 2s aggregate all of their recent transactions and represent them in a single Ethereum transaction? Well, that Ethereum transaction must contain a fair amount of data, essentially a summary of all of the L2's recent activity. And here's the problem. Ethereum only has one kind of data storage: permanent. When an L2, or anyone else for that matter, posts a bunch of data to Ethereum, everyone in the Ethereum network must hold on to that data forever. That isn't easy to do, and it places a significant burden on the computers in the network. That isn't good for Ethereum, especially because its priority has always been minimizing the burden on those computers to keep the network decentralized. The situation is also not good for the L2s. Ethereum doesn't want people filling blocks with data and overwhelming the low-end computers, so it charges a high price for data storage. As a result, L2s must pay a lot of money to make their settlement transactions on Ethereum, and the L2's users must pay higher fees to account for that. Again, this is particularly silly when the whole point of L2s is to provide a low-fee environment for users. And so, we need a better solution for storing data, and that is where Proto-Danksharding comes in. Proto-Danksharding, officially named EIP 4844, will introduce a new type of transaction to Ethereum, and these transactions will unlock a new kind of short-term storage. These new transactions are called blob carrying transactions, and believe it or not, blob is a technical term. It's short for binary large object, which basically means an arbitrarily large chunk of data. So when we say blob carrying transaction, we just mean a transaction that is associated and travelling with some piece of data. Data that might, for example, summarise a whole bunch of L2 transactions. But the word blob is also quite appropriate here. I find it useful to think of these data chunks as literal sticky blobs that cling to the outside of an Ethereum block like a barnacle on a boat. And just as barnacles are scraped off of boats and discarded before they cause problems, these blobs will be scraped off of blocks and discarded before they overwhelm the network. This is the big improvement that Proto-Danksharding will bring. Any data contained in a blob will only be stored on Ethereum for a few weeks. After that, everyone in the Ethereum network is free to delete and forget about that data forever, reducing the burden on all of those devices. It's safe to do this because that information doesn't need to be stored for eternity, at least not by all parties. The important thing is that the L2 data is distributed and made available to anybody who might need it. Sticking it onto the outside of an Ethereum block and distributing it across an uncensorable global network is a pretty good way to ensure that everybody interested has access. Then, after a few weeks, those interested parties should have had plenty of time to make permanent copies or to do whatever they need to do with that data. Blob carrying transactions are a big win for Ethereum. The short-term storage minimises the strain placed on the Ethereum blockchain and doesn't threaten its decentralization in the way that permanent storage might. It's also good for the L2s. Because short-term storage is less burdensome than permanent storage, a greater quantity can be offered at a much lower price. Therefore, Layer 2s don't need to pay anywhere near the costs that they currently pay to settle on Ethereum, and they can pass those savings on to end users. Overall then, it's clear that Proto-Danksharding and blob-carrying transactions are a massive step forward for Ethereum and its layered scaling ambitions. But you might be wondering, what has any of this got to do with the whole KZG thing that we started with? Well, we're about to find out. We've just seen that a blob carrying transaction is a transaction sent alongside and associated with some arbitrary piece of data. As well as travelling together, the transaction and blob are associated through a special reference or summary that is embedded in the transaction. It's worth noting that because it's part of a transaction and included in an Ethereum block, this reference does become a permanent part of Ethereum's history, even after the blob itself is discarded. That reference is something called a KZG commitment to the blob. Well, more accurately, it's a versioned hash of a KZG commitment to the blob, but that's not super important here. KZG commitments and commitment schemes in general can be used to prove ownership or knowledge of some information without revealing the information itself. Later, after the information is revealed, the commitment could be used to authenticate that information. That authentication would fail if there was even a single tiny difference between the information committed to and the information revealed. In the case of Proto-Danksharding, KZG commitments give users an efficient way to verify that blobs contain all of the information they supposedly contain and that L2s aren't misbehaving. KZG commitments can also prove that a certain piece of data was contained in a blob. This is essential for a type of L2 called an optimistic rollup, as they rerun disputed transactions on Ethereum to verify the results. Of course, there's no point rerunning a transaction that never actually took place on the L2, which is where the KZG proof comes in. When someone raises a dispute, they must also provide the KZG proof to show that the disputed transaction took place and was included in a blob. KZG commitments were chosen over alternative commitment schemes for several reasons. For starters, they're simpler to implement than the alternatives. That reduces the opportunity for errors or exploitable weaknesses to make it into the code. They're also fairly cheap and efficient to work with, which helps Ethereum's drive for decentralization. They work well with zero-knowledge proofs, which is essential for a type of L2 called a ZK rollup, and perhaps most importantly, they lay the foundations for another future upgrade called data availability sampling. There are really only two notable downsides for KZG commitments. First, they're not quantum resistant. So there could be security issues if someone develops a powerful quantum computer. Frankly, that's not worth worrying about today, and when it does happen, there will be so many other things at risk that it probably won't matter much then either. The second issue is more immediately concerning. KZG commitments require something called a trusted setup. And this is where the summoning ceremony comes in. Now, I don't want to get too bogged down into how KZG commitments work for two reasons. First, I just don't have the math skills to properly understand and explain them. And second, even if I did, I suspect you probably don't care anyway. Still, I think it's useful to have some vague idea of how KZG commitments work, so here goes. To generate a KZG commitment, the data being committed to is first converted into a polynomial. You'll probably remember these from maths class as equations that look something like this. In this case, The polynomial will be much bigger and scarier than anything you encountered at school, but it's essentially the same thing. That polynomial is evaluated at certain points, which is to say some numbers are plugged into it to see what comes out, and the stuff that comes out is the KZG commitment. When somebody wants to verify that data later on, they can effectively repeat the process. By evaluating the polynomial at the same points, they can see if the output matches the original commitment. If it does, everything is fine and the data was the same, and if it doesn't, then something has been changed. Now, here's the bit that's most relevant to us. The numbers that are plugged into the equation should remain secret. Like, really secret. Not even the developers setting the whole thing up should know what these numbers are. And if somebody did know what they were, they could cheat the whole system by crafting a new polynomial that produces the same output. In other words, they could commit to one set of data, then change it entirely but still provide a valid proof. This would, quite obviously, undermine the entire system, and so it cannot be allowed to happen. This raises some questions. First of all, how can those numbers be kept secret, but also passed around and used by anybody to commit to and verify data? And second, how can we trust that those numbers are genuinely secret? After all, somebody had to come up with them, and how can we know that they don't know what those numbers are? Let's start with the first question first. How are these numbers kept secret? Well, for clever mathematicians, this is fairly easy. The answer is to use something called an elliptic curve. Elliptic curves are a special family of curves defined by equations that look like this. If you plug some numbers into that equation and draw the results on a graph, the curve you would see would be an elliptic curve. These curves have some weird and unique properties that make them particularly useful in maths, computer science, and cryptography. In fact, a whole bunch of important cryptography, including much of the cryptography in this industry, relies on elliptic curves. The properties we care most about are that points on an elliptic curve can be added together to produce a third point that is also on the curve. When this is done, it's difficult to predict where the third point will be. And when the points are repeatedly added together, it's incredibly difficult to determine how many times the points were added. Mathematicians can use this to hide numbers inside the elliptic curve. Essentially, they take their secret number and add elliptic curve points to themselves that many times. The output of this calculation is a long list of elliptic curve points that appear totally random when plotted on a graph. This list of points is called a structured reference string, and an attacker could study it to their heart's content without ever learning anything about the secrets held inside. However, quite amazingly, the structure reference string still contains enough information about the secret values to be useful in constructing KZG proofs. That answers the first question. Ethereum can hide its secrets inside an elliptic curve. The secrets can be represented and passed around in the form of a series of elliptic curve points, a long list of seemingly random and disconnected numbers that is also known as a structured reference string. These numbers contain enough information for the KZG scheme to work, but not enough information for attackers to undermine the system. But where does the structured reference string come from? Who produces it? And how can they reassure others that they don't know the secrets held within? The answer here is to use something called a trusted setup. And the principle of it should be pretty familiar to anybody who is interested in crypto assets. After all, this industry's entire purpose is to remove singular trusted entities and replace them with large, disparate networks of individual operators, thereby increasing the overall trust in the system. Yes, the idea of a trusted setup is to involve as many people as possible in crafting the structured reference string. So instead of one person contributing the entire secret and then promising they don't know what that secret is, a trusted setup involves a large number of people, each contributing a small portion to the overall secret. Each individual contribution is cleverly mixed in so that nobody could determine what anybody else has added. That way, even if somebody knew exactly what they had entered, they wouldn't be any closer to discovering the ultimate combined secret. In fact, the only way to discover the combined secret would be for every single participant to work together to recreate it. Put another way, provided the group contains at least one honest actor, the final secret can never be known. This is called a 1 of n trust model. Alternatively, you might like to think of it like a Horcrux trust model. An attacker must discover every single secret, like destroying every Horcrux, to beat the system. The larger the group of contributors, the more difficult that task becomes. If Voldemort had created 1,000 Horcruxes, he probably wouldn't have been beaten. And that's kind of intuitive, right? The larger the group gets, the probability that it contains at least one honest actor also increases. And so the goal of the trusted setup is to maximize the number of honest and independent actors. At some point, when enough different people have contributed to the setup, the trusted setup becomes effectively a trustless setup. That's why some people prefer to use a different and arguably less misleading name for them. For example, Ethereum's trusted setup is called a Summoning Ceremony. Whatever you want to call them, trusted setups have been around for a while now. Zcash held the first high-profile setup in 2016. That was a fairly complicated and involved process, and so the ceremony only included 6 very knowledgeable participants. Modern setups tend to be simpler and more accessible. enabling hundreds or even thousands of people to take part. Ethereum's Summoning Ceremony will be the biggest setup yet, and by a massive margin. More than 120,000 contributions have been made so far, easily making this the most trusted setup ever. Now we understand the principle, but how does the Summoning Ceremony actually work? Well, it's kind of like a game of pass the parcel played backwards. In this case, the parcel is the set of elliptic curve points, and by played backwards, I mean each player is adding something to the mix rather than removing it. And as you can probably guess, the thing being added is the participant's secret random number. In the middle of it all is a sequencer or coordinator who keeps everything organised and running smoothly. For the KZG ceremony, the coordinator is a server run by the Ethereum Foundation. It keeps track of who wants to participate, orders the participants, and then verifies their contributions. If the ceremony is a game of pass the parcel, then perhaps the coordinator is a parent overseeing the game and ensuring it's played properly. Of course, the idea of a special, powerful entity at the heart of the ceremony may concern you. If so, don't worry. We'll come back to this in the next section. For the moment, I want to go a little deeper into how each participant in the ceremony adds their random number to the mix. When a participant joins the ceremony, they generate their secret random number. Later, when the coordinator says it's their turn, they receive a long list of more than 4,000 numbers. This is a set of elliptic curve points containing the combination of all previous participants' secrets. Now the participant can mix their secrets in as well, and they do this through multiplication. They take their secret number and essentially just multiply each of the elliptic curve points by that number. Well, okay, it's a little more complicated than that. In truth, they multiply by their number to a power according to where that point is in the list. So it's to the power of 0 at the first point, the power of 1 at the second, the power of 2 at the third, and so on. Plus, importantly, this is all done over something called a finite field, which work a bit like a clock in that they get to some maximum value and then loop back around to a lower bound. That means that two numbers can be multiplied together to produce a smaller number. Still, it's all essentially just multiplication. Once they've done that, they discard their secret and send the updated list of numbers back to the coordinator. The coordinator performs a quick validation and then sends the list on to the next participant to repeat the process. I found it useful to see this written out a little more mathematically. With some generic equations, the process looks like this. The participant receives a bunch of elliptic curve points that can be written like this, where G is some generic starting point for the elliptic curve being used, and S is the combination of all previous participant secrets, which our participant doesn't know. The participant then randomly creates their own secret value T, which they can multiply in to produce this. And this is equivalent to this. From this, we can see that the final secret produced at the end of the ceremony is just the product of every individual participant's secrets, and each elliptic curve point is related through those secrets, despite appearing as a random selection of numbers. As long as each individual keeps their secret to themselves, it would be extremely difficult to determine what numbers were multiplied together to produce the final set of elliptic curve points. In fact, because finite fields keep everything looping around, it's impossible to work it out. Participants in the Summoning Ceremony will be doing this for 2 sets of elliptic curve points each time. That's because the KZG scheme actually requires 2 sets of related but slightly different points. They will also do this entire process 4 times over, as in 4 entirely different setups with 4 different pairs of elliptic curve points, each of a different length. This is part of Ethereum's plan to future-proof things as much as possible. In the future, it may be desirable to make certain changes to blobs, changes that would necessitate a longer set of elliptic curve points to produce secure commitments. If that happened, a new ceremony would be required to produce those new points, creating unnecessary delay and hassles when it comes to that. So Ethereum's developers had an idea. Why not run multiple setups at the same time? That way, everything is ready and waiting if and when those changes are made. Earlier, we saw that the Summoning Ceremony relies on a special entity called a coordinator that keeps things running smoothly. But to somebody interested in crypto assets, that might raise some alarm bells. After all, doesn't the coordinator sound like exactly the kind of privileged central player that we want to eliminate? Of course, the answer is yes. The coordinator is certainly a privileged party, and I'm sure it would have been eliminated if that were possible. Unfortunately, it's quite essential to the ceremony. However, the coordinator's powers are quite limited, and all of its actions are published for everybody to inspect and verify, which should minimise the threat it poses. The worst thing the sequencer could do is unfairly exclude a participant. For example, it could incorrectly reject their valid contribution, but because its actions are published, everybody would see that happening and know the ceremony was compromised. Additionally, there will be a validation process at the end of the ceremony. Every participant will be able to verify that their contribution was genuinely included in the final product. This transparency is incredibly important. If anybody raises any genuine concerns at any point in their setup, the social consensus will be to reject the ceremony and start over, making any changes necessary to prevent the problem from happening again. As a result, I don't think the coordinator poses a real threat to the procedure. Realistically, the only other threat to the ceremony is some massive technical failure. For example, a bug might cause every participant's secrets to leak. If that happened, then it would be possible to reconstruct the final secret, regardless of the number of honest participants. However, the chance of this happening is extraordinarily low, especially because a lot of effort has gone into minimising this risk. For starters, there are multiple implementations of the contribution software, and they're all built using different technologies. For every contribution to leak, the same bug would have to be present across all of those different variations. It would need to work on every type of device, on every browser, every single time the process runs. In short, it's totally unrealistic. And yet, there are even more protections in place. In addition to allowing standard contributions through the browser, people have also been invited to make special contributions to the ceremony. In special contributions, participants can generate their secret random number in all sorts of wacky and weird ways. For example, they might use a Geiger counter, a cat toy, or an explosion as a source of entropy, though presumably not all of them at once. The point is, however those numbers are generated, it's utterly inconceivable that they could all leak in the same way as the standard contributions. And remember, that is exactly what needs to happen to truly undermine the ceremony. As long as a single number remains unknown, then the final output of the ceremony also remains secret. So I think it's safe to say that the summoning ceremony secret is safe and sound. Getting involved in the KZG ceremony is extremely easy, and the requirements are very low. You will only need 3 things. The first is a computer to contribute from. Unfortunately, mobile devices won't work here. The second is a valid browser, which seems to be anything other than Safari as far as I can tell. And the third is either an Ethereum account that had made at least 8 transactions before January 13th, 2023, or a GitHub account. These restrictions were put in place to try and prevent massive Sybil attacks. When the ceremony first opened, the lobby was flooded with thousands of airdrop farmers all trying to contribute from multiple addresses. Well, that's not necessarily a problem, it was limiting the number of genuine unique users that could take part. And so the rules were adjusted to try and ensure that everybody taking part was a somewhat unique human. So if you meet the criteria, then read on to see how you can contribute. Head to ceremony.ethereum.org and click Begin. A new tab will open. This is where you will generate your secret random number. As the page explains, the randomness comes from 3 sources. The first is called the secret, which is whatever you type into the text box. This can be as long or as short as you would like. The only suggestion is that you try to add something a bit random into the mix, so even you don't know what you've written. The second source is called the sigil, which is taken from your cursor's movements. And the third is called the sample, which your browser generates in the background. So type something into the text box and squiggle your mouse around. You'll see the serpent's tail growing longer as you move the mouse. You need to keep jiggling until the serpent eats itself. Then you can click Submit. You'll be asked to sign in. As mentioned earlier, you can either use GitHub or your Ethereum address. If you use Ethereum, it will ask you to sign a couple of messages from Sign In with Ethereum. Don't worry, this won't cost you anything or take any assets from your wallet. It's just signing a message. But, as you should every time you sign a message, just take a moment to double check that everything looks legitimate. The hard work is all done now, and all you need to do is wait. Just don't close the window or switch off your computer until you receive a confirmation message. The screen will tell you how many others are in the waiting room with you. The coordinator will make a random selection from this room when choosing who goes next, rather than selecting in any kind of first come, first served basis. That makes it impossible to know quite how long you'll have to wait. When I initially contributed earlier in the year, it took several days before I was selected. But at that time, the waiting room generally contained several thousand people. The waiting room today is much less full, so I'd imagine the waiting times will be measured in hours at worst. This time through it took less than 10 minutes. Eventually, the screen will change to let you know that you have received the structured reference string, here called the powers of Tau, and that your secrets are being mixed in. The screen will change again once your calculations have been completed and the coordinator has received your updated structure reference string. When this happens, congratulations, you have contributed to Ethereum's next upgrade. At the time of recording, there are just a couple of days left to get involved in this. The ceremony will end at the end of the 23rd of July. At that point, I would imagine they will just close the lobby for new entrants. So if you're in there at that point and still waiting to contribute, you should still be able to get it in. But to avoid any disappointment, it would be better to get in as soon as possible. If you're on the fence about contributing, I would definitely recommend it. It's incredibly easy, and it's nice to be able to say that you are a part of this special moment in Ethereum's history. Whether you contribute or not, I hope you enjoyed this video and found it useful. I'll put a link to the summoning ceremony in the description below, as well as links to some further reading on KZG schemes if you want to go into the nerdy details of them. And with that, I will say thank you very much for watching. I know I haven't done a video for quite a long time now, But I did do some written-only pieces on Medium and on Mirror last year, so if you're interested in checking those sorts of things out, I'll put a link to them in the description below, and you can subscribe there if you're interested. But again, no worries if you're not. Have a great day, and I will see you in the next video.